Okay, welcome back. In this video we will talk about the unit testing. Testing as such is super important, therefore that will be a very important lecture and unit. In order to do everything which I'm showing here, you have some prerequisites. You have to install pytest and coverage with the pytest banding. If you didn't do that, you can do it in Conda easily from the command line. So please do that now so that you can follow the exercises. So let's talk about program testing first. Why do we do program testing at all? So basically one scenario which you can think about that's very important when you are writing a program. You are checking whether the program works as is supposed. Then you are extending and refactoring the program. And again, you have to check whether all the functionality which previously have worked as good as possible, whether they are still working, right? So are the old features still functional? And of course, this is something which you have to do every time you are adding something and changing code. The other scenario which is where testing is important is when you're writing your program and you check this functionality, but then you distribute the program to somebody else, to some other users. And the question is, okay, does the program work in their environment as expected, exactly in the same way as in your environment? You cannot be sure because they might have a different environment than you, different numerical libraries, and therefore it's very important to have tests which can check that the program also in that environment works as supposed. So basically we can ask the questions, okay, so we have some testing routines, some testing functionality, when do we have to invoke it? And of course it's super important to invoke it after each relevant change you make. So whenever you make something which changes the code, you should try to test whether it still works as supposed. And of course, whenever it is used in a different environment, so basically in an environment which was maybe not considered during the development, has different libraries or different numerical behavior. So the question is, okay, when we know when to test, how to test, and very important to me, the most important is we all are lazy persons, so basically the effort should be as low as possible. So basically it should be also fast so that it doesn't take long, and it should be very easy to start, and of course it should be automatic. If you think about that, if you have, for example, big matrices, you definitely do not want to compare them just by looking at the screen. The comparison should be made automatically. So it's very important that basically the automated testing with a certain test protocol so that you can see what happens is a part of the development. And the important point is it should be automated. Now, what kind of possibilities you have here, or what kind of tests you can make? We can make, and there are two different test definitions I would like to mention here. The first one is the unit test. Exactly, this is what we were doing here today. Sometimes it's also called white box testing. So basically each program unit or each usually a function or a class is tested independently. So basically we are testing for a function whether a given input gives the right output. So we are testing very small parts of the code. There is a so-called regression testing as well, when you are testing your package as a whole. So typically you are just providing the user supply data, if the user input in some form, and you are looking at whether the output which is generated is the one which is supposed. So you are basically testing the entire package as such. A very important term which you should maybe also think about, get more deeper into that, is the so-called test-driven development, which is part of the agile programming paradigm. And here basically you write first the tests and only then implement the functionality. The nice thing with that is that if you write a test first, you exactly know what are the expectation basically the certain algorithm is going to fulfill. So basically through the test you are specifying the functionality of your program, and then you program as long as you don't fulfill all the tests. If a bug is found, for example, in this test-driven environment, then basically you would not fix it immediately, but you would first write the test, and then basically if you have a test which basically reproduces the bug, then you would fix it so that make sure that the test passes again. Okay, how can we do that in Python at the end? There are two different ways, or the most commonly used ways in Python is either to use the unit test package in Python, which comes with Python itself, or using the pytest package, which is a third-party module, but basically it's a very standard thing, and many projects use it as well. We will in this video and this session basically talk about the pytest packages and the package, and the reason for that is that it's very easy in pytest to write a very small and straightforward test. The unit test package which comes with Python is also very powerful, but requires an object-oriented approach. Pytest can also work very nicely in a procedure in function-oriented approach. So let's have a look. Let's assume we have a mathematical library which contains a few mathematical routines which we wrote. And one of those routines is a very simple routine which just calculates the factorial of a given number. And now the question is, how can we write a test for this routine? And if you use pytest, it's super simple. There are basically only two things you have to consider. So that would be the module which is basically testing the mymat module. I am importing the mymat module so that I can access all the functionality of my module, and then I have defined here two test functions. You can recognize that by the fact that the functions start with the prefix test underscore, and this is exactly, it's very important. Every test function, every test must start with the test underscore prefix, because this is how pytest will recognize that this is a test function. Then I am just calculating here, for example, here the factorial of 5. I am just storing it in a variable of result, and then I have an assert, and this is the important point here. I have an assert which checks whether the result is 120, which it should be. Why is this assert important? This assert statement in Python works as follows. If the bool expression which stands after the assert is true, then nothing happens. If this bool expression is false, then the program would stop. Actually, in pytest, the program would not stop, but it would indicate pytest that the test failed. The same, if I want to test here for the factorial of 0, I am just calculating the factorial of 0, and then by an assert, I am testing whether the result is equal to 1. If this comparison here, this bool expression here, is true, nothing happens. If it's false, if it turns out to be false, so the result is not 1, then basically it would signalize the pytest framework that this test failed. So just to here to repeat, you should make sure that you are starting with a test prefix, and you should use an assert, and the boolean expression, and the bool expression should be false if the test is supposed to fail. That's it basically. So how can I run my test? Basically, there are two different ways to do that. One way is just you are doing it directly from the shell. So basically in the Linux shell, the git bash shell, you are just starting Python, and you are starting Python with the -m option, and you are writing pytest. That would mean that Python is started, and immediately the pytest module is imported. If you are using git bash on Windows, then you have used, of course, as always, Python instead of Python 3. What will happen if you just start Python and importing the pytest module? The pytest module starts a so-called test discovery. So basically it will analyze the files in the directory, and if it finds a file which contains routines which start with the test prefix, then it will just execute them and test what happened. And if it executes, it finds our test math routine with the two or file with the two test functions in it, and then they are executed, and none of the asserts failed. So basically both tests passed. You can also run it from Visual Studio Code. Basically you should first invoke the Python config or tests from the command palette. Then basically you have, of course, select pytest as the framework, and if your test solver .py or test_mymat.py test file is in the root directory, then you should, of course, select the root directory, definitely not the pycache directory. If you do that, afterwards you can just select the menu Show Testing, and if you do that, there will be the bar on the right hand side with the tests, and then here you have a few icons in order to run the test. For example, with here you could run all the tests, and then you would see the result here in the bar. And of course, if there's a check, it means that the test was successful. You can also mark, basically, you see it also here. You have also next to the test, if you have the source code of your tests here on the screen, a check or something else, depending whether this test was failing or not. And if you click on that with the right click, then you can basically even select individual tests and run only those sets. So basically, it's very nicely integrated into Visual Studio Code. Actually, talking about the test file and whether it's the same directory as the source code for the library for the module or not, the usual convention is that the tests are separated from the actual library, from the actual code you develop. And the usual convention is that you are creating a test subdirectory, and all the test related stuff are put into that test subdirectory. The good news is that pytest can still discover them. So basically, if you are invoking pytest from the root project folder, even if you put either this way or that way, depending on which system you are, even if you put your test files into the test folder, it will nevertheless find it and then execute all the tests. Some other tools, and also among others Visual Studio Code, needs some more help in order to locate the test function, the tester, correctly if it's in a test subfolder. And basically the help it needs that you have to create an empty file here in the test folder, which is called __init.p. So basically you have twice underscore and then init, and then init.p. So this is one. This is not a long score button, but 2 underscores. That's important to note. And basically this is just must be an empty file which is in this test folder. That's it. And if you do that, then also Visual Studio Code will able to locate the tests. And if you are saying running all tests, then it will be able to import the appropriate modules and run them. Okay. Another thing I would like to show you is the so-called parameterized test. And this is something we need when we have several times we want to use the same test to execute the same test, just maybe with different input data, but otherwise the algorithm for the test is the same. Now imagine just testing our mymat module, and within the mymat module the factorial function. And of course we had before a different function which just checked the factorial of 0, whether it's 1. It was also checking the factorial of some other number, let's say 4, and whether it's 24. And it would be a waste of time and a lot of copy pasting to write an individual routine for all of them. So much easier is if we have just one routine, a so-called parameterized routine, and then we are passing this parameterized routine, the different scenarios, the different pairs here. In every pair, in every tuple, the first number basically tells you what is the input, and the second number is what is the expected output. Now how can we do that? The first thing is that we have to create a so-called decorator. I won't go into the details what decorators are. Just note here for the moment that decorators are starting with the add character, and then you are using the pytest mark parameterized decorator, and you are passing it 2 different arguments. The first argument tells what is the name of the parameter, and this name we just call them factorial. And in the function, in the test function, that we will have an argument with exactly the same name, with the name factorial. Okay, and then basically what pytest will do, that the next argument I have to give the parameterized markers or decorator is a list or something pytest, an iterable actually, something pytest can iterate over, and basically every value of this iterator will be passed as to the test. And the good thing is that basically for every value of this list, pytest will create different tests, but each test will do exactly the same algorithm. So basically from the factorial, which is a tuple, it will just extract the first and the second element into the variables num and result, and then it would call the factorial function with the num value, and check whether it's equal to the result value. And of course, as we learned already before, it is put into an assert to make sure to signalize pytest if that the test failed if this bool condition is a false. And with that, it's very easy because we have to write the algorithm only once and we just feed it with different data. Another scenario one could think about that if the tests are, let's say, reading this data from input and output files. So if you think about, for example, a project what you are doing in these lectures with the solvers, with the linear solvers, I could just collect the names of the different test cases as a list. I could just create files with different names which contain the input data, so the A and B matrices, and the output data, the X vector, which is the solution. And then I would have to write only one routine, again using this decorator, the pytest mark parameterized decorator. I would here call the parameter just test name, and I would just pass it the list test name so that it can run over all the values of test names. And if you just write a routine, let's say get test input, which for a given test name reads from a file A and B, and we could write a routine get test output, which for a given test name reads in the X vector, then basically our routine would just call the Gaussian eliminate solver and store the result in Xgauss, and then it would check whether Xgauss is close enough to the expected value. So basically A and B are read from file, also X expected is read from a file, and Xgauss is calculated. So, and the good thing is that if I'm adding newer and newer tests to the system, where just the elimination should be checked, I can just extend this list and add further elements, but I don't have to touch the code anymore, which is doing the testing, because the algorithm is exactly the same. So it can be super easily extended. And of course, we should not forget again that it needs a decorator. Now, if we have all the tests, the question is, do we have enough tests at all? And one of the possibilities to find that out, or one of the possibilities to quantify a little bit how good our tests are, is the so-called test coverage. And the test coverage basically tells us the relative amount of the code lines relative to the total code lines which have been executed during the tests, right? So if you have tested really every line of your code, and this is the desirable quantity, you would have a test coverage for 100%. Please realize that even having 100% test coverage doesn't mean that your code is bug-free, because it only means that every line has been executed. But of course, whether the data which was used or not, it has to do something with the realistic data which the user will use. You don't know. So you have to make sure that your tests have a big variety. How can I get this coverage information? I can use the coverage tool in Python, which can collect this information. And basically from the command line, I can start a test differently as before. I can just start the coverage tool. Then I'm passing the command run. Then I'm passing it the - source equal dot argument. It's very important because it should not test any of the modules which I import. It should only test the modules which I wrote, so which are in the directory or below that where my project is. And I will test coverage coverage just to import the pytest module at the start. And then of course, if that pytest module is imported, as we have seen before, it makes an auto discovery and we run all the tests. If you run it, then basically it very much looks like before. There is not much difference. Maybe the only thing which you note that the plugins, you have no the CAV plugin. This picture is an older one using an older Python version, so the CAV version would be newer in your case, but there is no other difference. Okay, so then what is the purpose of this entire exercise? We can visualize actually the coverage data which was just recorded during this test. And you can, for example, say coverage report -m, then you get a short summary of the coverage information. And here you have how many statements you have in the mymat module. And very important, here you have statements means a line, how many lines were missing by the tests. And apparently here, no lines were missing, so the coverage is 100% for the source file. If some of the lines would have been missed, then you would have a number here. So for example, if line 2 would contain code which were not executed during the test, then you would have here a number 2, but this is here not the case. Fortunately, our project has 100% of test coverage. You can also visualize this data, which can be very, very useful. You can again use the coverage tool and pass it the HTML subcommand, and then you are specifying a directory which will be created, and all the HTML information, web information will be put into that directory. And if you just open basically with your browser in the coverage HTML directory, the index.html file, then you get a similar information as before, however, in a graphical representation. And here I'm showing it from a different project, from a solver project. This solver project has a solvers module which should be tested, and it seems that it had 25 statements, but one is missing. So I have only a test coverage on 96%, and then I can click basically on the link solvers, and then it would open basically the source code of solvers.p. It will tell me how many lines were run, how many is missing, and basically it will mark with a red bar what was the missing statements. And in my case, apparently none of the tests included a case where this if statement was true. That means that none of the tests in my case include the linearly dependent system. So with that, you can find out whether there are lines you are not testing for, and you should make sure that your testing coverage is as high as possible, ideally 100%. Okay, before we finish, I would like to show you a few functions which are quite important when we are comparing, and helpful when we are comparing arrays with each other. For example, in the solver project, we are just making a numerical solver, and we want to compare array solution vectors with each other. And I would like just to remind you what we already discussed when we introduced arrays, that if you have an array, and for example, you are comparing an array against a scalar value, like whether an array is smaller than 0, then basically you get not one bool value back, but you get basically an array of bool value back, where for every element in the array you get the result of the comparison, right? So basically arrays are always compared, or arrays are always compared element-wise. If you want to reduce it to a single bool, then you have many different options. One option is using the mp.any function, and that would be basically true when any of the elements, at least one of the elements, if the array is smaller than 0. So if this is what you are looking for. You can use the mp.all function, which would give true only if all the elements are fulfilling the criterion. So here again, I'm checking whether a is less than 0, and basically mp.all will give false, because it's not true that every element in the array is smaller than 0. This is only one element, so it would be false. And mp.var can be also quite nicely used if you want to not just compare, but basically choose different values depending who the elements in the array are. And mp.var, how it works, here you have basically a condition which gives true or false for every element. For every element where there is a true value obtained, this value will substitute, in this case 0. For every other element where the comparison value was false, the original matrix element from A will be substituted. So basically this line tells me every element which is smaller than 0, please replace it with 0, otherwise leave it as it was, and you get exactly, if you compare this, the -2 was the only element which was smaller than 0. It was replaced by 0, all the other elements remained or kept their original value. Okay, and one even more important thing is which you should keep in mind when you are comparing floating point values, right? So basically the numbers which are using the dot notation. So basically the rule which you have to remember is never ever to compare floating numbers with the equal operator. So please never do that. I will not go into the very further details why. You should actually have a good book or good introduction to numerical mathematics. The only thing you should here remember that floating point representation is not necessarily exact. For example, if you take here 0.1, which is basically has only 2 digits in a decimal system, but our computer works in a binary system, and in binary digits it would require infinite number of digits to represent this number. As a consequence, when you are working with quantities where the representation is not exact, there are numerical errors which occur during floating point operation. What does it mean? Depending on your system, on my system already, if I check whether 6 times 0.1 is exactly the same as if I'm just adding up 0.16 times, and then of course if you do exact mathematics it should be exactly the same, but the equal operator will say false. And why? Because you are doing a different numerical error on the right hand side than when you evaluate the left hand side, and the two floating point numbers are not exactly the same. They are very close to each other, but they have not the identical value, and therefore you will get false. So how can I compare then floating point numbers? And the way to do that is that you are comparing them with tolerances. So that's basically the solution. What does it mean? You are not checking whether the two numbers are equal, but they are close enough to each other. You can, for example, calculate the absolute error. Then you are basically not doing nothing more, just subtracting the two numbers from each other. You are taking the absolute value of that just to make sure that you get a positive number, and then you are checking it against a tolerance value, and if it's smaller than a tolerance, then they are close to each other. If you would do that for an entire array, then we can just use the mp.all function, which we learned before, in order to check whether all of the items are in absolute value close enough to the reference value. We can also compute the relative error, which can be very important in certain cases, where basically we do the same as before. We are just getting the difference of the two elements, but also divided by the value of the reference element. If you do it for an entire array, then again we can just use the mp.all statement in advance. And finally, one can also combine the two kinds of errors, and maybe this is the best thing to do, is the mp.isClose, so the numpy module has an isClose function, where you have just basically the one quantity, the reference quantity, and you can specify a relative tolerance and an absolute tolerance, and then it will calculate a combined error and gives you a yes or no, whether if the two errors or the tolerances are basically fulfilled. If you want to look it for an entire matrix, then you can use the all close instead, which is the equivalent, and then it would give you true if it's true for all elements. Okay, and with that, basically you are now in the position to write your third unit test and tests your Gaussian elimination module. Thank you.